Assalamualaikum and salam sejahtera. We are from KK12. I'm Muhammad Firdaus bin Ismail and my fellow member are Yolid Kin, Anis Syuhada and Nur Hajatul Akmal. So, today we want to present about our final year design project. The theme for our final design project are production of raw material from renewable resource and non-alcoholic based hand sanitizer. From this theme, our title for final year design project are production of sorbitol from dry empty food branch. Our supervisor are Prof. IR Dr. Muhammad Sorbita Krif and IR Dr. Teo Yik Han. And our industrial supervisor are Muhammad Fitri bin Lias and Ridwan Afandi Abu Bakar.
Assalamualaikum and greetings to all. My name is Nur Hajatul Akmal binti Muhammad Halifah, and today I will be presenting about the introduction. Based on the theme given, we decided to produce sorbitol as our main product. Based on the International Cosmetic Gradient Dictionary and Handbook 7 edition stated that sorbitol is used in non-alcohol hand sanitizer and act as humectant with the range between 1% to 8%. Sorbitol is a sugar alcohol and has the role as sweetening agent, a laxative, and also a humectant. The table on the left side shows the chemical and physical properties of sorbitol. As for our raw material used, we decided to use dry empty fruit branch (EFB) from the waste of the palm oil, as we already did the comparison between three types of raw material, which is EFB, pineapple waste, and coconut coir fiber. We compare from the cost and the glucose content, as our main process will be using glucose which undergoes hydrogenation process to produce sorbitol. And based on the comparison, we found out that EFP contains higher glucose and low cost. Thus, EFB is selected for our raw material. Next, this is the other usage of sorbitol. The usage of sorbitol can be classified into three main industries, which include food industry, cosmetic and personal care industry, and medication application. Next, we move to the supply and demand. The graph shows the supply and demand of the sorbitol, and by referring to the supply and demand of the sorbitol, we decided to build our plant with capacity 750 kg per hour or 6,030 tons per year, which covers 0.57% from the shortage of sorbitol.
So from here, I will talk about the profitability analysis. For the production rate of sorbitol at full capacity is around 6,030 tons per year, and our product sales price is 16 ringgit per kg. And then our MARR is around 20%, and from there we calculated our ROI, and that is 0.32 per year, which is larger than the MARR. So the project is profitable. And then for our payback period, it is around 1.62, and the payback period reference is around 3.51, which is larger than the payback period. So the project is also profitable. And then for our average net return, it is around 15.2 million per year, which is larger than zero or a positive number. And then our MPV is also positive with 143.7 million per year. And for our DCFRR, it is also larger than the MARR with 0.47. And then on the right side, we have our break-even analysis graph of it.
The figure above shows the level to input-output structure. The input consists of EFB, water, hydrogen gas, carbon dioxide, and sulfuric acid, while the output for our process is sorbitol, wastewater, hydrogen gas, methane, lignin, hemicellulose, xylose, levulinic acid, and HMF. This figure shows the level 3 conceptual design, which is the main process unit in our plant, which include pretreatment unit, hydrolysis reactor, and hydrogenation reactor. Level 4 conceptual design is a step of synthesis of chemical separation system. The separation units that involved in our process is centrifuge, fractional distillation column, flash drum, and evaporator. This figure shows our process flow diagram before heat integration. As raw EFB enters the plant, it will undergo a pre-treatment process. This process purpose is to break down the EFB into lignin, hemicellulose and cellulose using supercritical carbon dioxide as the catalyst. After the process, carbon dioxide will recycle back into the tank and the other output product will then enter hydrolysis reactor. The hydrolysis process will use 1 mole of sulfuric acid in a continuous stir tank reactor with a ratio of solid to liquid 1:10. The purpose of this process is to convert hemicellulose and cellulose to xylose and glucose respectively, while lignin will not convert and just stay as solid lignin. Levulinic acid and HMF is produced as side product in this process. The outlet stream will enter the first separation unit, which is centrifuge, where we want to separate unwanted component, which is lignin and unreacted hemicellulose and cellulose. The next unit is the second centrifuge unit to remove the excess solid before entering fractional distillation column. This column will separate all the components based on the boiling point. The first top product is levulinic acid and HMF. The second top product is sulfuric acid and it will recycle back into the hydrolysis reactor. The third top product is xylose and it will be stored into storage tank. For bottom product, which is glucose, it will then enter hydrogenation reactor. The process is called hydrogenation process, where it uses hydrogen gas as a reactant to convert glucose into sorbitol. The reactor chosen for this process is fixed bed reactor. Next, the output product from hydrogenation reactor will enter flash drum to separate the excess hydrogen gas from the liquid products. Finally, the liquid products will enter evaporator to remove excess water to obtain the pure product, which is 70% sorbitol. Next figure is our process flow diagram after heat integration. The energy requirement before heat integration is 1484 kilowatt. After performing heat integration using pinch analysis, the energy requirement is 1454.6 kilowatt. The total energy recovery of this process is 1.99%. This is our piping and instrumentation diagram. The type of controller that were being used is temperature, flow rate, pressure, level, and composition controller.
As we move to the safety analysis part, we started with the acts and regulations that comply to the plan. The first one is Environmental Quality Act, EQA 1974, and under this act, there are three main acts that we comply, which are stated in the slide. And next one is Occupational Safety and Health Act, OSHA 1994, that consists of Safety and Health Officer Regulation, and we comply this regulation as our plan is a chemical industry that will be having 100 employees, and the engineering construction where the price of the total contract is higher than Rm 20 million. Next is the use and standard of exposure of chemical hazardous to health regulation 2000. This is because our plant will be using hazardous chemical, which is high concentration of H2SO4 and high pressure of hydrogen gas and carbon dioxide gas. So we can comply this regulation to our plant. We will also comply the Control of Industrial Major Accident Hazard 1996 regulation. We comply this regulation due to the high flow of carbon dioxide use that may cause explosion due to its overpressure. And it is a major hazard installation (MHI) since the quantity hazardous substance used is higher than threshold quantity. Our quantity hazardous substance for carbon dioxide is 21 times, while the threshold quantity for carbon dioxide is only 10 times. And lastly, we also comply the Factory and Machinery Safety, Health and Welfare Regulation 1976. So this is the hazard analysis for the whole plant that consists of the hazard identification, risk assessment, and risk control. Risk level is obtained by the risk metric by using the equation risk equal to severity times with the likelihood. Okay, next, this is our proposed plant location. There are three proposed plant location, which is Kawasan Perindustrian Kelapa Sawit Kuala Johor, Kawasan Perindustrian Sindayan Tanjung Valley, Negeri Sembilan, and Kawasan Perindustrian Bercan Ipoh Perak. So these are the criteria that we consider, which is the raw material supplier, road infrastructure, water supply, power supply, land size, land price, and the climate. Next, for the selection of the plant location, we will be using the vector scale, which consists of 1, which is not suitable, 2, slightly suitable, and 3, which is suitable. And we will do the score rating, and by the score rating above, the kawasan perindustrian kelapa sawit Pulau Johor obtain the highest score and become our primary site location for our plant setup. Okay, so this is our plant layout. We build our plant in kawasan perindustrian kelapa sawit Pulau Johor, and we already consider a few safety aspects for this plant layout. For the first one is the main production area is located near to the storage area to reduce the piping cost and to ease the transportation of the substance and materials. The next one is the main production area is located far away from the administrative area, which is to minimize the risk. And the wastewater treatment is located near to the production area to ease the transportation of the waste. And lastly, our expansion area is located in the main production area for the future expansion.
Next, I will explain on waste management. The table above shows the flow rates and composition of each component in waste stream. For liquid waste, the organic matter present in effluent is HMF and levulinic acid. The value of concentration, COD, BOD, and suspended solid concentration for both HMF and levulinic acid is stated as above. For waste gas, the component present is hydrogen gas and methane. After we calculate the concentration of the gas for an hour in ppm, both gas have lower concentration than the standard limit, so the gas can be purged. This figure is the process flow diagram of wastewater treatment plant. Since our organic matter is non-biodegradable, it will undergo chemical treatment first, then biological treatment. For chemical treatment, the effluent will enter reactor and then separator. The process involved is called wet air oxidation, where air is used, then separator will separate the off gas. After that, it will enter equalization tank and sent to coagulation and flocculation tank, where flocculant is added to clump small particle into bigger lump for easier removal. Then, it will enter first clarifier to remove sludge. Next, the effluent will enter aeration tank to remove excess COD and BOD. Finally, it will enter second clarifier to remove excess sludge. Finally is the waste minimization step. There are 3 steps that we propose for our plant. The first is use the solid waste produced after pre-treatment as energy sources for the process plant. Second, improve the quality in production process by doing quality control checks. And finally, reduce the lead time when turning the raw materials into final product.
For conclusion, our plan designed based on the sustainability concept, which is focused on the environment, economic and social impact. So we use the renewable resource, which is an empty fruit bunch from oil palm refinery for production of sorbitol. The environment is actually clean since we use the empty fruit bunch as our main component for production of glucose under hydrolysis process, and the glucose will undergoes the hydrogenation process for production of sorbitol. This design plant is able or generate the income based on the production of sorbitol and xylulose. The plant capacity for our production, which is the main production is production of sorbitol, is 6,030 tons per year. Thank you.